Energy in simple harmonic motion. We have two types of energy. We have the kinetic energy and potential energy. And in simple harmonic motion, this energy are present. So first, let's define kinetic energy. We know that kinetic energy is energy in motion, and it can be solved by having the product of the mass and square root of the velocity divided by 2. And in terms of potential energy, since we are dealing or we have illustration of ideal spring, we have now the formula for the elastic potential energy where the symbol is U is equal to the half of the product of the spring constant times the square root of the displacement. And we have the total mechanical energy is equal to the sum of the kinetic and potential energy. And in any system, the energy, the total energy is being conserved. Therefore, the sum of the kinetic and potential energy is always constant. Here is the illustration of the relationship between the energy and the displacement. Starting here at the middle drawing, at the initial position of the body, we have the total kinetic energy is equal to the total mechanical energy, which means our potential energy is 0. And as it moves to the right, we have the potential energy partly increases and the kinetic energy is partly decreases up to the point it reached to its maximum displacement or the amplitude wherein that the total mechanical energy is equal to the maximum potential energy. Same way in the same way, when our body is at the negative amplitude or at the left, we have 0 kinetic energy and all the potential energy is equal to the total mechanical energy. Now, to further understand the relationship between the motion and this energy, we will have a simulation from O physics. So here's the simulation of ophysics.com and the link will be posted at the description below. We have here an object that is attached to a spring and moving in a frictionless surface. And we have the energy pie graph and the energy graph and the time graph. And we have set the initial spring stretch of 5 at 5 unit, which means the amplitude is 5, the mass at 10, and the spring constant of 80. So let's run the simulation. So we can observe how the energy changes, how the potential energy converted to kinetic energy, and the same way kinetic energy being converted to potential energy as our body is moving back and forth. And also in this time graph, you can see that not only the position oscillating or has a periodic motion, but the velocity, acceleration, potential energy, and kinetic energy are also oscillating, meaning it has a sinusoidal graph. You can observe at position 0, the kinetic energy is at its maximum and the potential energy at 0. And at maximum amplitude, the potential energy is maximum and kinetic energy is 0. Now going back to our slides. So now let's try to solve problems involving the energy and a simple harmonic motion. So we have here a problem. The figure shows an object of mass 0.2 kilogram that is vibrating on a horizontal frictionless table. The spring has a constant of 545 Newton per meter, and the spring is stretched initially at 4.50 centimeter and is then released from rest. Determine the final translational speed of the object when the final displacement of the spring is 2.25 centimeter and 0 centimeter. Now, solving the problem, we know that the total mechanical energy is equal to the sum of kinetic energy and potential energy. Therefore, we have E is equal to K plus U. Plus U, wherein K is equal to 1/2 mv squared plus 1/2 kx squared, which is equal to 1/2 ka, which is constant. So in our problem, since we are looking for the final speed or final translational speed of the object at position of 2.25, we can have this formula. Vf squared plus 1/2 k x squared is equal to the initial, since we have a constant energy, plus 1/2 k x squared. And we can cancel out this one because we know at Mach the initial is 0 at rest, since it started at rest. And kinetic energy in the XFO is 0. Okay, so we can cancel out this because the the velocity at the maximum displacement is equal to 0. Therefore, we remain with this 1/2 mv f squared plus 1/2 kx f squared is equal to 1/2 kx squared. And we cancel out the halves na constant. Therefore, by simplifying this one, we can have Vf is equal to the square root of k over m times x all squared minus xf squared. So using this formula, we can solve now for the maximum velocity. For the final translational speed. So for part A, we have Vf is equal to square root of 545 Newton meter over 0.2 kilograms times 0.045 squared meter squared. Let's put bracket here, minus 0.0225 meter squared. Okay, therefore, our final translational velocity is equal to 2.03 meter per second. Part B. So at 0, what is the final translational velocity? So applying the same formula and substitute the value of 0 at xf, therefore Vf is equal to 2.35 meter per seconds. Okay, so that's it. So try to solve our test or understanding problem.